And thanks for the very kind introduction and the invitation to participate today. Really excited to be here. I'm going to talk about some developments in what we now call deep learning, what we all used to call neural network modeling, that I think are pretty exciting on the topic of architecture, neurocognitive architecture. And it's all about this thing that I want to call the compositional turn. So just to set the scene, of course, there's a great revolution going on over the last decade or so in neural network research, arguably kicked off in 2012 with this breakthrough result on image classification using convolutional neural networks. But then, of course, just one amazing thing follows another from there. We have things like DALL-E from OpenAI, which takes a caption like an armchair in the shape of an avocado, and then almost magically spits out these beautiful images of newly imagined chairs in the shape of avocados. Of course, in the realm of deep reinforcement learning, we have superhuman play in games like Go and chess, video games like StarCraft, and then even scientific applications like protein folding are using deep learning now. A lot of excitement quite recently has been focused on large-scale language models, and since I'm going to talk about those as a sort of focal point, it's worth just sharing with the entire assembled audience here how impressive these models have become. Many of you will have seen this sample from OpenAI's GPT-3, but just in case you haven't, let me just read at least the beginning of it. So the idea is that this language model is fed in a bit of a language context, and then it has to complete, like it has to spit out a completion for that initial prompt. So the prompt here was, in a shocking finding, scientists discovered a herd of unicorns living in a remote, previously unexplored valley in the Andes Mountains. Even more surprising to the researchers was the fact that the unicorns spoke perfect English. And then the language model generated all of the rest autonomously, and it begins, the scientists named the population after their distinctive horn, Ovid's unicorn. These four-horned silver-white unicorns were previously unknown to science. And it goes on later, in a later paragraph, to talk about which scientists discovered them, the sequence of events, the fact that they speak English and why that is. It's really, people are starting to pick these models apart, but I think by any standard, this is an amazing thing to see from deep learning. Having said that, I think those of us who have been playing with neural networks long enough to be aware of their history before 2012 sometimes have to marvel at the degree to which all of these recent developments really had their roots in work 25 years ago. And when I say had their roots, I mean a lot of the very specific things that people are excited about right now were already underway back then. So convolutional neural networks were first proposed in 1998 and were trained with backprop. Deep reinforcement learning had its first, its first working system back in 1995, applied to backgammon, and even language models are actually pretty old. So you can go back to Ellman in 1991, who used recurrent neural networks to do next word prediction exactly the way that GPT-3 does next word prediction. Of course, a lot has happened in the interim, and I'm not trying to minimize the breakthroughs, but it is still pretty remarkable what the resemblances are between what was going on 25 years ago and what's going on now, except with, of course, the great exception that we have much larger and faster computers in order to investigate the potential of these techniques. However, having said that, there is another side to what's going on in deep learning these days that I think is fundamentally new, and that's the thing that I really want to get into. And to set the scene for this, I just want to recall, some of you will know this pair of papers from 2010, which was a bit of a kind of debate across two papers between two communities doing computational modeling of cognition, the connectionists on the one side and people doing Bayesian modeling on the other. And really, like, the point of contention in this debate was about how to build systems that capitalize on structure. And what structure means really is compositional structure. Structure in the data, structure in behavior, structure in perception that can be regarded as being made up of building blocks. The way that words are combined into sentences is compositional, and there are many forms of compositional structure of that kind across many data domains that are relevant to cognition. And the importance of compositional structure was emphasized as a challenge for deep learning as recently as 2015 and 17 in a very influential pair of papers by Brendan Lake and colleagues, where they really stress, like, human cognition capitalizes on compositional structure. If somebody showed you this picture of this weird unicycle motorcycle, you could immediately understand what this thing is by cobbling together things that you know about segways and motorcycles and unicycles and taking the relevant bits and putting them together in a compositional fashion. And this work by Lake and colleagues focused on the simpler example of how people can understand the compositional structure of novel glyphs. And in their papers, they proposed that in order to really get at this aspect of cognition, you need to do something quite different from deep learning. You might need to resort to symbolic methods. This is a challenge for deep learning. And if you go back again 25 years and look at particular pieces of work from the connectionist literature, you can see people wrestling with this. So, Ellman's work was arguably addressed to how we can handle compositional structure in language. There's a very influential paper by Jeff Hinton, we lovingly called the family trees model, that took a different approach to compositional structure by suggesting that different vector representations of names should be associated with particular thematic roles. And there's also work from spelling to sound that used attractor networks to try to explain how people can read non-words in a way that is sensitive to the phonotactic constraints of the relevant language. And I wanted to also point out this work that Randy did on the cognitive neuroscience front, trying to address that same problem. How is it that we can how is it that our brains handle compositional structure here in the domain of language? How do we know that the words Bob ate steak that combination of words means Bob ate the steak rather than the steak eating Bob? And this is a fundamental problem in cognition, and one that honestly deep learning systems, as they were dreamt of in 25 years ago, really did struggle with. And this is where I think there's been a set of really important and sort of, from my point of view, rather fundamental innovations in deep learning over the last, really just the last 3 years or so. And these innovations are at the level of architecture. And the architectures that I have in mind here include graph neural networks and another architecture that I'll focus on, which is called a transformer. Those of you who keep track of the deep learning AI literature will know that transformers have been kind of a craze, starting with language modeling work, but now applied across many domains. And there's a reason why. They're really special. They bring to bear an architectural bias that favors compositional processing. So for those of you who aren't familiar with transformer architectures, just a couple words to give you the intuition on what they're about. They take in a set of vectors. So the input data is already divided into discrete units. So in the original applications, these were representations of individual words. And then there's a stage called self-attention, where a set of dot products distributes an attentional filter across each of these words. And the way it works is that each word or each input vector attends to all of the other vectors and then updates itself in a way that folds in some information about what its neighbors are. And so you feed in a set of vectors, you do this self-attention or cross-attention step, and then you end up with a set of output vectors that are sort of inflected or informed by those lateral attentional operations. And then you can do this recursively, feeding it into another round of self-attention and so forth. So these networks are really good at handling compositional structure. What I mean, by the way, by compositional structure is a set of discrete elements. So the most obvious example would be words, but as we'll see, you can use other kinds of discreteness. A type token distinction, stable building blocks that are nonetheless inflected by their context, and thematic role assignment in the sense that we were just talking about it. I think there are some really interesting implications of these architectures for neuroscience, understanding brain architecture. I'll just mention very briefly what my own kind of musings about this are. There are some very interesting transformer architectures that use recurrent connectivity. So they start with this set of input vectors and they put them through this self-attention operation, but then they go back and feed the resulting vectors back into that same layer and do this recursively in the form of a recurrent neural network. And that means that these systems have essentially two kind of motifs in their connectivity. They have a lateral connectivity motif, which is about this cross-attention or self-attention operation. And then they also have a recurrent connectivity motif. And of course, those are both very much familiar elements of large-scale brain architecture. I think that's just sort of an intriguing parallel. Okay, so this is the architectural innovation that's led to these sorts of amazing results in language models. But what I think is most exciting now, given the current state of play in the AI literature using architectures of this kind, is to go from composition, where you're taking a set of given building blocks, say words, and learning how they combine, to now kind of panning back and also figuring out how these kinds of systems can also decompose data. So using these systems now to identify discrete components in, say, high-dimensional data that can then be subjected to this compositional operation that we've just been looking at. And so let me give you one example of how the work is already emerging that addresses both sides of this combination of operations. And that is the discovery and then computation based on physical objects, visual objects. So when you see this painting, your visual system, as we know from a great deal of psychology research, parses it into discrete objects and then represents the whole thing in terms of relations among those objects. How is that happening? How does the visual system discover those objects? And there's really cool work emerging now from the AI side that gives us a handle on how unsupervised learning might do that. So one of the first systems that I'm proud to say came out of DeepMind is nicknamed Monet. And without being able to go into detail here, the basic idea is that there's a neural network that learns through dealing with a rich set of visual images to spit out mask functions. And then there's an autoencoder that takes in the mask function and is tasked with reconstructing the input image, but it's only responsible for the regions that aren't masked. And then this is a multi-step process with each step unmasking an additional piece of the image. And an unsupervised learning algorithm tasked simply with that set of operations discovers the objects that make up each of these images. So what you're looking at here is the original visual images that were sent into the system, reconstructions of those images, but then a representation of the objects that were pulled out individually from the source images. And below you can see reconstruction of individual objects from the source images. And cool things happen like deocclusion. So if the network is asked to reconstruct this one sphere, it reconstructs the whole sphere, even though the sphere was occluded in the original image. That was a system that was introduced a few years ago. To update that, some people in my group at DeepMind just put on arXiv a paper that does a bit more. It takes video inputs and decomposes those through unsupervised learning into discrete objects, but also a set of latent representations that distill out what's going on at a particular point in time. So you can combine a set of object latents with a particular frame latent, like frame of a video, and you can reconstruct, for example, the point of view, the camera angle that was in place at that particular moment in the video. I'm going to skip over the details. We can come back to them if people want to know about them, but I'll show you how the results pan out. So again, through unsupervised learning, the system learns to parse input videos into discrete objects, which it then tracks. And it learns a set of object latents that allow you to individually manipulate discrete objects in a particular scene, but also a set of temporal latents that capture things like what the camera angle was. And you can get the system using these latents to imagine the same scene from a different angle. Okay, I'm going to speed through the remaining results because they're really there to just give you a sense of what's possible now. But let me just now transition to the question of, well, what would you do with these object representations? Now that we have unsupervised learning algorithms that can discover them, is that useful in some way? And the answer is a resounding yes. So one example is visual question answering. There's a data set called Cleverer that was introduced last year that has videos like the one represented here with objects sort of colliding with one another and passing one another in space, accompanied by a set of questions that AI systems are tasked with answering that range from really simple questions like what shape is the object that collides with the cyan cylinder to really complicated questions like without the gray object, which event will not happen? And it turns out that if you take a transformer exactly like the one that I described before that was developed for doing language processing, but you feed in not only the words that make up the questions in this data set, but also alongside that, a set of discrete object representations, which here were generated with that Monet system I mentioned a moment ago. And then you train the resulting system on a subset of the questions that come from this data set. Skip over that detail. You get pretty amazing results. This is just a sort of comparison table across a set of neurosymbolic models that had been proposed for this data set and our own system nicknamed Allo. And you can see it's doing surprisingly well, even compared to these highly structured neurosymbolic models that often get privileged information during training. And it's really the object level representation that makes the difference. If you remove that component, the performance really craters. You can look at where attention is distributed in these models, and it makes perfect sense. We can come back to these results if people are interested. There are other interesting data sets that require tracking of objects even when they're obscured or hidden under other objects. We get state-of-the-art results there with the same setup. There are a cool new data set called Acre, which riffs on the developmental psychology literature. Some of you will know about like the Blickett experiments that Alison Gopnik pioneered. This is sort of a machine learning data set equivalent of that. And here again, this simple transformer architecture that takes objects and words as inputs does an amazing job compared to other state-of-the-art models. So that so far is just question answering, but we see similar results in reinforcement learning. So some of you will know this work that I mentioned earlier on StarCraft, the video game StarCraft, used object level representations and in fact fed them into a transformer model, and that was one of the secrets to the system's success. We have done some other work, which I don't really have time to get into, but I'm happy to talk about it during discussion, that shows that there are, however, limitations to the ability of deep learning systems to do discovery of compositional structure. And again, I'm running out of time, so I'll just give you a flavor of what this work was about. It's a video game style task called Alchemy, where the agent has to transform a set of objects using these magical potions in order to gain a maximum number of points. But the underlying chemistry keeps changing from each time you play the game. And the task of discovering structure here is about learning the latent structure of the task. And what we find with state-of-the-art deep RL models is, compared to an ideal observer model, a Bayes optimal model, whose score is indicated here, deep learning systems do terribly on this task. Their behavior is basically random. They don't seem to make the right inferences at all about what's going on. So maybe this is another domain where using high-level discretizations of the data would be useful, something that we're planning on trying. There are other architectural innovations going on that support discovery of latent structure. Again, happy to get into this. It's something called the perceiver architecture from Jagel in our group. But since I don't want to use up all the time for discussion, I'm just going to power on to acknowledging my collaborators on all these little pieces of work. I just want to give a shout out to Rashab Kabra, who led the way on that, that video parsing model, Simone, David Ding, who led the Allo project, Jane Wang, who developed Alchemy, and Drew Jagel, who developed the perceiver architecture, which I was only able to mention briefly, but happy to discuss. And thank you.
Thank you so much, Matt, for this impressive presentation. And thank you for being like essentially powering through and being on time. We have quite a few interesting and thought-provoking questions in the chat. I'm gonna collapse two of them, taking some liberties here, into a single one that I would like to ask you right away. And these are questions that were posed by Antonio and Moan, and essentially come down to the idea that couldn't you use like classic approaches to do this segmentation? And is there really much more than classic segmentation? And wouldn't you need anyway some kind of ground truth to understand this, this compositionality anyway? So what is the deep learning really adds?
Okay, so I'm not familiar with classical methods that do instance segmentation in this particular way. There are a lot of supervised systems that do this kind of object identification. For the most part, they don't address the problem of how you segment images that involve totally unfamiliar objects, but under generalization that it's not unimaginable that would happen. But the more interesting point is about, whether you can do this without ground truth information. And the answer there is yes. The systems that I described get no ground truth information at all. The only data that they see is these unsegmented images. What's important is that the images contain enough variety, for example, showing particular objects in very many positions adjacent to very many other objects, so that the model then has a pressure from the data set to compress the data in a particular way. The intuition is that the internal structure of objects is compressible because the internal structure of objects is familiar. The information about which two objects happen to be adjacent in a particular image is less compressible because it's so highly variable given the combinatorics of the visual world. And so that's really the key that allows this kind of segmentation to happen in the totally unsupervised case. And that's why at the heart of this Monet model is a variational autoencoder that essentially has an information bottleneck that encourages compression. So that's a very compressed explanation, but the short answer is yes, this is possible without any ground truth.
Okay, thank you very much. We have a few extra minutes for a couple of questions. And again, I'm going to try to compact a couple of questions at a time to save time and answer as many as possible. So there's a question that I have and a question that Pat Langley posed, which comes down to essentially the debate between connectionist and symbolic architectures. And maybe not doing Pat Langley justice about this, but isn't putting these architectures and this constraint in the structure of the networks a way to essentially like introduce symbols through the architectural constraints?
Coarsely, yes. I mean, I do think of it that way. So it depends on what aspect, like what you think the defining aspect is of a symbol is. I'm just looking for my transformer picture here. Yeah. So one thing that's very important is the type token distinction, right? So transformers make it easy to handle situations where you have two instances of the same entity, which depending on the architecture that you're dealing with, can otherwise be difficult. There are also the symbols interact if you consider these input vectors to be symbol-like, then they compose in a fashion that can be very similar to the way that symbols compose in like classical symbolic systems. In fact, people have used transformers in order to learn to solve integration problems, like mathematical integration problems. or to do to learn where to put closed parentheses given open parentheses, to do code synthesis. So the answer is yes. However, there are a couple of ways in which transformers and related architectures, there's a couple of things that they add. First of all, they impose a kind of inductive bias toward compositional processing, but they're learning systems. So they don't tell you necessarily what the symbols need to be. And they also, so you can induce the appropriate symbols from the data if you have the right setup. And the other thing is that because they're neural networks and these inputs are vector formatted, then you can retain all of the benefits of distributed representation, similarity-based computations, and so forth, which of course were always the strength of deep learning. And so I see this not necessarily as turning deep learning models into symbolic systems, but instead finding a kind of workable middle ground where we have some of the strengths of symbolic computation, but still retaining some of the strengths of neural networks.
Thank you. We have two more questions that I would like to pose from you that come from the chat. One is from Robert West, and can you comment on the relationship between transformer networks and holographic memory models?
No, I can't do that. I mean, I'll take the coward's way out and simply unpack the question by acknowledging that holographic memory, of course, was one of those methods that was proposed over the last 25 years, specifically to deal with compositional structure. I don't know whether anybody has done the work to try to map between the self-attention operations that occur in transformers on the one hand and the relevant computations in holographic representations. That would be a fascinating thing, but I certainly don't have a ready answer. Perfect.
And we have one question from Randy, and I think this is a perfect question to bridge between your two talks. And is, do you have any thoughts about larger scale neural architecture corresponding to the transformers in terms of things like PFC, hippocampus, or basal ganglia?
Well, yeah, this was one kind of weak shot at it, in the sense that if you focus in on transformer architectures that do this, that use this kind of recurrent connectivity, and I should mention this is not the general approach, but there is a family of transformer models that do this self-attention operation in a recursive way. Then I find it intriguing that you have these kind of closed loop circuits through basal ganglia. The kind of classical Peter Strick closed loop cortical basal ganglionic thalamic loops. And that might give us this might give us a hypothesis about what those circuits are doing. They're basically implementing the nonlinear step that's so important for transformers, whereas the lateral connectivity within cortex, like across hypercolumns or stripes, appealing to some of your own previous work, Randy, might be implementing something like this self-attention operation that takes local representations and shades them in a way that takes into account the larger context. The only other thing I'll add to that, and this is all very impressionistic, I'll acknowledge. I think that's a great area for new research. I mentioned this new transformer architecture, and the cool thing about this architecture is that it reserves a set of latent vectors where discrete representations can be learned from the data. So in the original transformer applications to language, you have input units, input elements, which are words, right? They're lexical items or like essentially morphemes. In this case, you have those input vectors, but you also have another set of latent vectors that are kind of free to be whatever they need to be in order to solve the assigned task. And this feels to me a little bit like one cortical area attending not laterally within itself, but attending to another cortical area. And so this maybe gives us a thread to pull on in order to understand hierarchical connections between cortical areas. So again, that's totally impressionistic and maybe wildly out of line with the empirical, like, with what really is going on in the brain. But I think it's an interesting possibility to investigate.